Hey, in the past second you spent watching this video, roughly 46 new websites, 8 hours of YouTube videos, and 4.6 petabytes of data have been uploaded to the web, and the amount of data we generate will only continue to grow. With all this information, it can get pretty overwhelming to find the most relevant, up-to-date information. This is why search engines and recommendation systems have become vital in finding the content we are most interested in. But even they have their limits. When dealing with millions or even billions of candidates, it can be hard to narrow down the most relevant results in a short amount of time. One reason for this is the k-nearest neighbors problem. To put it simply, many information retrieval methods search through large datasets to pick out the closest points to a query. For example, they could return web pages that match a search prompt, or movie recommendations that match a user's watch history. In other words, they must find the top k-nearest neighbors that match a query. Now you could look through every single piece of data to find the closest results, but this is painfully slow when working with millions of data points. So what computer scientists have done instead is to approximate the closest points. These approximate nearest neighbor, or ANN algorithms, trade accuracy for speed. HNSW, one popular ANN algorithm, is 380 times faster than KNN search. But what if we could go even faster?
This is exactly what we explored. Now, if you don't know anything about HNSW or hierarchical navigable small words, think about them as multi-layer graphs where the more layers you descend, the more details you see. We can hop along these HNSW graphs to find the data closest to any kind of query, so long as we can map both the data and the query onto the graph. But this method does come with a few catches. Mainly, we need to calculate the distance between the query and all the data points in and around the path to the query. This may be easy in 1 or 2 dimensions, but what about if we work in 960 dimensions? Distance calculations get very expensive as data complexity increases. So we try to minimize these calculations in 3 ways. First, we took some HNSW graphs and removed their unimportant edges, so we don't need to look at their distances anymore. Second, we tried alternate conditions to stop the search when we got good enough results. At last, we skipped around the HNSW by zooming in on multiple parts of the graph at the same time. In each case, our goal was to skip unnecessary distance calculations to improve performance. As these methods get more refined, we hope that HNSW and similar ANN algorithms will get even faster and keep up with our ever-growing sea of data.